Hello and welcome to the Terran Space Academy, where we help prepare you for a bright future in the space industry. Please don't forget to stay connected and tell us what you like. And help us out on Patreon if you can. We appreciate you. SpaceX has been a very innovative company, and there is no doubt that it has advanced rocket science more than any organization since the days of Apollo. Many people are quick to point out what SpaceX gets wrong, which is okay. That's how we learn from the mistakes of others, in the hopes of avoiding them ourselves. But it's unfair to ignore what they get right. Let's take a look at SpaceX Innovations, and especially Raptor engine design. Here is a SpaceX Starship on stage 0 with the launch tower. A launch mount is nothing new. Here is a Soviet N-1 launching from one. This is a stationary launch mount with flame trenches. But the SpaceX system of starting all these engines on the outer ring is unique and innovative. We'll call this Innovation Number 1, reducing the mass and complexity of the rocket itself, since these 20 engines are only needed at launch and don't have to be restarted. Rockets are brought to the pad horizontal after being assembled in this position, and are then lifted vertical before launch. The Soviets often used trains to move their rockets. Americans chose to assemble their rockets differently from the Soviets. This is a vertical assembly building, one of the largest buildings on Earth. The massive Saturn V was assembled here on a mobile launch stand. This giant crawler would then lift it and carry it out to the launch pad. The crawler would then leave, and the rocket would be fueled by quick disconnects supplied by this tower and associated ground support systems. Most U.S. rockets launch from Florida and use water deluge systems to moderate sound waves and protect the launch pad. SpaceX now does the same thing after creating their famous rock tornado. They somehow thought it might not be necessary before. This could be called glaring error number 1. But the second launch went smooth, and I think they have this worked out. This launch tower is unique in one way. SpaceX uses very small crawlers to move out first the booster, which is then lifted by these arms, often called chopsticks, onto the launch mount. This is a unique and innovative design not seen on any other launch system. We'll call this Innovation Number 2. Now let's look at the rocket itself. The Starship rocket system is made of stainless steel. That is not unique. The solid rocket boosters on the shuttle were made of steel, and the Centaur second stage is still made of steel, and many older rockets were made of steel. There are many reasons to use this metal even though it is denser than aluminum or titanium. One of the main reasons is cost. Titanium is lighter and very strong, but it is expensive and hard to work with. Aluminum is a completely viable choice, used here in these massive shuttle tanks, and here in the even larger Energia system. But aerospace alloys are also expensive. By the way, I had someone point out that the Starship was not the largest object ever sent into space, that these are, and I agree. But these are the equivalent of giant empty soda cans. While the Starship is a fully reusable spaceship with a mass of over 1,300 metric tons, I don't think it's a fair comparison. Now, aluminum has a much lower heat resistance than steel, and these giant tanks were not used for anything at all in space. They burned up on re-entry. An important factor, if you plan to reuse your rocket, is the heat resistance of the underlying metal. SpaceX had looked at carbon fiber, which is an excellent choice for small and medium rockets, but it's very hard to make carbon fiber hold on to liquids, especially cryogenic ones. Rocket Lab has worked out a way for their liquid oxygen and kerosene systems, but for something as large as Starship, it would probably be necessary to have a metal tank inside your carbon fiber, and then where is your benefit? Rocket Lab plans to build the much larger Neutron out of carbon fiber, and we'll see how well that works. Aluminum is not very heat resistant, and neither is carbon fiber, and carbon fiber is extremely expensive. SpaceX decided not to make a single perfect, non-reusable, ultra-expensive rocket like the SLS, but instead wanted to make a durable space truck, capable of countless flights. Steel was the obvious choice. Choosing methane as a fuel was unique, as it had never been used in an operational rocket system before, but its potential had been pointed out as far back as Robert Goddard. So while steel and methane are innovative choices for Starship, the concepts are not new inventions of SpaceX. But then we come to the Raptor engine. We've covered this engine in multiple lessons, but in short, it is a full-flow staged combustion methane-fueled rocket engine. Full-flow staged combustion was not invented by SpaceX. The Soviet RD-270 was invented half a century before Raptor. It never flew, but was built and tested. What makes the Raptor rocket engine so unique is the extremely high pressure in the combustion chamber, beating the previous record holder, the RD-180, by a large margin. The other unique thing about the Raptor is the cost. The Raptor 1 cost about $2 million to build. It had a mass of 2,000 kilograms, a chamber pressure of 250 bar, a specific impulse of 330 seconds, and a thrust-to-weight ratio of 93. Compare that to the Space Shuttle main engine, which is also an amazing work of engineering achievement, but costs so much more as to be practically unavailable. Now here's the thrust of the Raptor 1. As most of you know, this is not how I like to report thrust. Here, if they mean metric tons, it should be spelled differently. A thrust of 185 tons is listed here. This means that this engine puts out the same force as a 185-ton mass would exert on a surface due to the Earth's gravity. Force is mass times acceleration. The force of gravity is 9.807 meters per second squared. We'll go with 9.8. But then we must also remember that the proper unit of weight is newtons. A metric ton is 1,000 kilograms. So we must multiply this value by first 9.8 and then 1,000 to get the correct units. So we should correctly say that the weight of this block is 1,813,000 newtons. We could report this in kilonewtons, 1,813, or roughly 1.8 meganewtons, which is the unit I prefer. And the force or thrust produced by this engine is also 1.813 meganewtons. So this engine could hover this mass against the force of gravity. Now using this shorthand can be intuitively useful, which is why SpaceX uses it. If we built a rocket with just one Raptor engine, we could look at this number and divide it by a useful thrust-to-weight ratio, usually around 1.5. And we would know that we could build a 123-ton rocket if we wanted a thrust-to-weight ratio of 1.5 with a single engine. A 123 metric ton rocket on Earth. Let's double-check this and use the proper units. The weight of this rocket is 1,205,400 newtons. The engine has a thrust of 1,813,000 newtons, and this matches. It's fine to use this shorthand in Earth's gravity, but on the Moon or Mars, these values are incorrect, since the force of gravity is lower. We said that our rocket on Earth would need to have a mass of about 123 metric tons to achieve a thrust-to-weight ratio of 1.5 on Earth. Gravity on the Moon is only 1.62 meters per second squared. That makes its weight on the Moon only 199,260 newtons. This engine on the Moon would generate a thrust-to-weight ratio of 9. 9 Gs can be hard on humans, and that would probably break ribs and possibly kill someone, especially if we're sending people that are not trained and extremely fit astronauts out there. Now let's look at the Raptor 2. This is what we saw fly on the first 2 integrated test flights. The Raptor 2 has more thrust than the Raptor 1, 24% more, at a cost of only $1 million, so half the cost. It is also 400 kilograms lighter. How did SpaceX improve the cost, mass, and thrust? You can easily see that it is much more refined. That will reduce the human time needed to assemble these rockets. Human time is the most expensive component of most industrial processes, and removing unnecessary systems and plumbings also makes it lighter. But how did they also make it more powerful? Here are the factors that help us figure it out. First, the pressure is 20% higher. What does the added pressure allow? Remember that the force a rocket engine produces is a factor of its exhaust velocity times the mass propellant flow. These numbers are not given here, but we can calculate them ourselves from what is available. force or thrust in this case equals m dot, mass propellant flow, times VE, which is the exhaust velocity, and we have F, the force. Now to calculate m dot, we need VE. Luckily, they gave us the specific impulse here. And we know that exhaust velocity equals specific impulse times 1 Earth g, the same number we used up here. Doing the math gives us 3,234 meters per second for the Raptor 1. Using that number and the proper unit of newtons, converting these to their base units and canceling, gives us a mass propellant flow of 560 kilograms per second. So these two pumps are sending a combined mass of 560 kilograms per second into the combustion chamber. To roughly figure out the relative masses of oxygen and methane, we just need to remember that the oxidizer to fuel ratio of a Raptor is about 3.7 to 1. Adding these together gives you a total of 4.7, with a relative percentage of 79% and 21%. Multiplying the mass propellant flow by the decimal equivalent gives us 441 kilograms per second for oxygen and 119 for methane. Now let's look at Raptor 2. There are two ways to increase the thrust of an engine. We can increase the mass propellant flow, or we can increase the exhaust velocity. The exhaust velocity is determined by the molecular mass of the products of combustion and the temperature of the combustion chamber. What we call temperature in this case is just a measure of average atomic and molecular kinetic energy. The temperature of modern combustion chambers is not that different from the Apollo days, as most high-temperature alloys like Inconel were discovered back then, and have not been dramatically improved upon. The lighter the molecules, the faster they go for the same equivalent temperature. So hydrogen rockets have the best efficiency of all common rocket fuels, with RP-1 rockets not quite as good, and methane being in the middle between these. Modern rockets use regenerative cooling and have pretty much maxed out the temperatures they can survive. If you can't increase the temperature, what can you do to get more thrust? We saw that 20% increase in pressure up here. Why is increased chamber pressure good for a rocket engine, provided it does not blow up? Chamber pressure is a measure of how closely these propellants are crammed together. This increases contact and therefore reaction rate. A faster reaction rate allows a shorter residence time. Residence time means the amount of time needed for efficient combustion to occur. Since thrust equals mass propellant flow times exhaust velocity, and the exhaust velocity is limited by the heat the combustion chamber can stand, SpaceX increased the pressure to reduce residence time and allow them to pump propellant through faster. How much faster? We can calculate that. But first, let's notice that the engine lost a little efficiency, going from 330 seconds to 327. Why might this be? Elon Musk has said that the throat of the rocket engine was modified. Remember that the throat is the opening from the combustion chamber to the nozzle. Here the propellant molecules are subsonic, here they are sonic, and here they are supersonic. So the throat turns heat and pressure into focused and directed kinetic energy. The throat is a crucial factor in a rocket engine. Too small, and it takes too long to get enough exhaust through here, reducing performance. Too large, and your reactants might go out too fast to completely combust. You can have a larger throat and maintain efficiency if you can increase pressure enough by pumping propellant in faster. Let's do that math now. Our new specific impulse gives us a new exhaust velocity of 3,205 meters per second, compared to the Raptor 1's 3,234. If we take the thrust here and turn it from rocket slang into real science numbers, we get a thrust of 2,254,000 newtons. Using this value, we get a mass propellant flow of 703 kilograms per second, an increase of 27%. So a 20% increase in chamber pressure, with a little modification in the throat, let us increase the mass propellant flow by 27% and thereby increase the thrust by 24%. This drop in specific impulse means they are sacrificing a little efficiency to optimize thrust. Why is thrust so important on the first stage? First, if the rocket's thrust-to-weight ratio is too low, the rocket will climb slowly. The longer it stays vertical, the more it suffers from something called gravity drag. Remember that being in orbit is all about horizontal velocity. Only the sideways velocity counts. Everything burned to get up and above the atmosphere is essentially wasted. The faster you can get up and horizontal, the less propellant you lose to gravity drag. The higher thrust also makes it possible to lift a heavier rocket. That means ultimately more payload to orbit, since delta V is determined only by starting mass, final mass, and exhaust velocity. The larger your starting mass, the more you can get to orbit. And the higher the thrust of your first stage, the more mass you can efficiently get up and on its way. But the Raptor 2 is not the end of the SpaceX Raptor engine's innovation. The rockets we saw fly were old technology, throwaways. They weren't the latest Raptor engine design. Here we see the stats for a Raptor 3, 3.1, and 3.2. These are the latest Raptor variants and are being tested right now. We see that the mass doesn't change, but the thrust definitely does, which increases the thrust-to-weight ratio for the engines. The current champion in thrust-to-weight rocket engines is the Merlin at 184, used on the Falcon 9 and Falcon Heavy, currently powering America's manned spaceflight program and producing profits for SpaceX. But if these numbers are correct, SpaceX has beat that record with Raptor 3. How did they accomplish this? Here we see that while the thrust is going up, the pressure is also going up, but the specific impulse is staying the same. And we know that means increased mass propellant flow, all the way up to 917 kilograms per second with the Raptor 3.2. How is SpaceX increasing their performance so dramatically? By aiming high. Elon Musk had talked about a new rocket engine quite a while ago that would not be called Raptor. It was referred to as LEET1337. Why LEET? Apparently it's a coding meme for LEET speak or internet speak, and 1337 is a kind of numerical palindrome for LEET or vice versa. I am not that fluent in nerd speak. At any rate, Musk set an almost impossible goal right after the Raptor 1 was developed. Reduce the mass to 1,100 kilograms, barely more than half the Raptor 1's mass. Get 320 tons of thrust, with a chamber pressure of 450 bar, pumping almost 1,000 kilograms per second through the combustion chamber without losing efficiency. SpaceX did not succeed in making this engine, at least not yet. But when you aim for the impossible, the point where you fail may be farther than anyone else has ever gone. And there is no doubt that rapid production and testing of Raptor engines is making huge progress. The amazing thing is that as the engines become more capable, they are getting remarkably cheaper. That will reduce the cost of each Starship dramatically, since the engines are the main expense factor. I would argue that SpaceX is not trying to build the perfect rocket right now. It's trying to build the optimal rocket production facility. And that is the pinnacle of rocket design, and the greatest innovation SpaceX has given us so far. The only goal of IFT-1 was to clear the tower and not destroy Starbase. The only goal of IFT-2 was to stage properly. Everything else for both flights was extra. Again, these were throwaway rockets. The ultimate goal of SpaceX is to develop a system capable of producing thousands of rugged and dependable starships. Only then can we move human civilization into the solar system. Now, many think this is an impossible goal, and maybe it is, but I would argue that all the world's hopes for a human future in space today depend on Starbase, because no one else is even trying. Thanks for watching, and stay safe. At Astra Pro Terra.
Attention all operators on countdown 1. This is the final go, no go for flight 2 of Starship. Again, our T0 is at 7 a.m. Central. Raptor 1.
Go.
Raptor 2.
Go.
Stage 1.
Go.
Stage 2.
Go.
Copy, go for flight. Clock is rolling. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. We have liftoff. booster engine cut off.